Hello, good morning everyone. This is Jaswinder Kaur and I'm here to teach complex analysis. Today I'm going to start the example which is very important and expected one. So contour integration theoretical expected examples. This assignment 4 is very expected. Remarks. I'm repeating some of the remarks because I'm going to use these remarks in this example. If fz has a pole of order k at z0, then residue of fz at z0 is equal to, you have to learn this formula because it is very important, 1 over k minus 1 factorial, limit z tends to z0, we have to derivate z minus z0 the power k f of z, k minus 1 times. Second, e the power iota sine theta minus n theta can be written as, by using the Euler's formula, this is cos of sine theta minus n theta plus iota sine of sine theta minus n theta. Now if I am going to write the real part of this exponential form, the real part of this e the power iota sine theta minus n theta, then this will be equal to, I have to delete this imaginary part. Sorry. So this will be equal to cos of sine theta minus n theta. Keep this in your mind. Alright, let's start with the example. Prove that integral sine from 0 to 2 pi e the power cos theta cos of n theta minus sine theta d theta is equal to 2 pi over n factorial, where n is belonging to the natural numbers. Now what we have to do is, limits are ensured, that is from 0 to 2 pi, okay and very fine, right? We have to make changes in this numerator. E the power cos theta cos of n theta minus sine of theta d theta, this will be equal to 0 to 2 pi e the power cos theta. Now because I know that cos of minus theta is equal to cos of theta, yes? Alright. Can I change the sign here? Can I write it as sine of theta minus n theta? This is one and the same thing, right? Alright. Next. Now I have to mention this in real part. So the real part of this integration is equal to this step. See, if I write instead of cos of sine theta minus n theta as e the power iota sine theta minus n theta, and I have to write here the real part of this, then I will be getting this integral 0 to 2 pi e the power cos theta into cos of sine theta minus n theta, and plus iota sine theta minus n theta will be deleted because I need only the real part. So if I write the real part of this thing, I will be get back to my step, this one. That's why I have written in the remark that the real part of e the power iota sine theta minus n theta is equal to cos of sine theta minus n theta. I have used this. Fine? Alright. This is equal to the real part of integral 0 to 2 pi. Now I'm going to separate the powers. This is e the power cos theta, e the power iota sine theta, e the power minus iota n theta d theta. Now I'm going to add this power and this power so that I can get again e the power iota theta as a power, right? So the real part of integral 0 to 2 pi, this is your e the power cos theta plus iota sine theta, right? and this is e the power minus iota n theta. Now I know that this e the power, now cos theta plus iota sin theta again can be written as e the power iota theta. And this is as it is. Now our integration is becoming very easier to calculate. We have to evaluate this integral now. Right? Everything is now cut and clear. We have to just put the value of z equal to e the power iota theta. From here I get d theta is equal to dz over iota z, and my circle is mod z is equal to 1. Whenever I'm going to put in terms of z, then I have to write here the circle C representing. So this is e the power, instead of e the power iota theta, I write z, and this is e the power minus iota n theta. So this is z the power minus n. D theta, instead of d theta, I'm writing dz over iota z. Is this clear? Is it fine? Alright. So this is equal to further e the power z. If I take z the power minus n to the denominator, this will be z the power n. And here also I'm having one z. So this will be z the power this n plus this 1. Right? And 1 over iota taking outside the integral and dz. Is it fine? Alright. Now I'm taking this whole to be as f of z. So this is f of z dz, where f of z is 1 over iota e the power z over z the power n plus 1. Now next step is to find out the poles for this function. So how I get the poles? By taking the denominator equal to 0. The denominator is z the power n plus 1 equal to 0. How many poles I'm getting? Of order? Yes, poles are having order n plus 1. Right? So I'm getting 0 n plus 1 times. So I'm having the pole of order n plus 1. And now I'm going to use the formula for this to calculate the residue, because I'm having the pole of order n plus 1. So for that, I know the formula is, alright, now z equal to 0 is falling inside the circle, mod z is equal to 1. So we have to find, clearly fz has a pole of order n plus 1 at the origin, and I'm going to find the residue for this fz at z equal to 0 having order n plus 1. So the residue of fz at origin is equal to, I know the formula, 1 over k minus 1 factorial, limit z tends to 0, we have to derivate z minus 0 the power k into f of z k minus 1 times. Now here k is n plus 1, right? So if I put n plus 1 over here, I will get n factorial. If I put n plus 1 over here, I have to derivate n times. And here it's already k, so this is n plus 1 and f of z. So let me write this. So this is equal to, this is 1 over n factorial, and this iota I'm taking outside. I'm having in iota f of z. Alright, first I will put the value over here. Limit z tends to 0, dn over dzn, z the power n plus 1 into f of z. Put the value of f of z over here. What is f of z? It is 1 over iota e the power z over z the power n plus 1. So 1 over iota I am writing outside. and e the power z over z the power n plus 1, which is cancelled out. So this is equal to 1 over iota n factorial limit z tends to 0. Now I have to derivate e the power z n times, and I know that always the answer is e the power z. Putting z equal to 0 over here, e the power 0 is 1. So I'm having 1 over iota n factorial. Finally, it is 1 over iota n factorial. This is the residue. So now applying the Cauchy residue theorem, we get this integral to be equal to f of z dz, that is equal to 2 pi iota times the calculated residue of fz having the pole of order n plus 1, which is lying inside the circle. So it is 2 pi iota times the calculated residue, and I have calculated the residue as 1 over iota n factorial. Iota is cancelled with this iota, and this will be 2 pi over n factorial. Now if you equate the real parts of this integral, you will get this is integration 0 to 2 pi. Now what is the real part for this e the power iota n theta? This is e the power, what is this? Cos theta plus iota sin theta, because I have to take the real part, so this will be e the power cos theta only into, from here this will be cos of n theta minus iota sin of n theta, because I have to take the real part only, so cos of n theta minus sin theta, right? D theta, that is equal to 2 pi over n factorial. Is it clear? Is it fine? Alright. Let's move on to the next example. This is very important. This is also very important. Prove that integration from 0 to 2 pi e the power minus cos theta cos of n theta plus sin theta d theta is equal to minus 1 the power n 2 pi over n factorial, where n is belonging to the natural numbers. Now here again, this integration, we have to make changes in the numerator, and also we have to write in terms of the real part of the given integration. Now limits are fine, that is from 0 to 2 pi, it is okay. And this is e the power minus cos of theta, and my first step is, because I know that cos of minus theta is equal to cos theta, so can I write this as with minus sign? Is it fine? Yes. Now this is nothing but the real part of 0 to 2 pi e the power minus cos theta e the power minus iota sin theta plus n theta. If you open this and taking the real part, you will get back onto the original integration, right? Furthermore, this is equal to real part of integral sin 0 to 2 pi e the power minus cos theta, and this is, I'm separating the powers. This is e raised to the power minus iota sin theta, and then e the power minus iota n theta. Now I have to sum up these powers, and I will be getting real part of integration 0 to 2 pi e the power minus cos theta plus iota sin theta, and e the power minus iota n theta d theta, so that I can take this as, this is e the power iota theta, right? And this is e the power minus iota n theta d theta. Very fine. So we will evaluate this integration now. This is equal to, we have to put z equal to e the power iota theta, and this is e the power minus e the power iota theta is z, so this is minus z into e the power minus iota n theta, so this is z the power minus n. Then instead of d theta, I have to write dz over iota z. And after that, this is integral over c e the power minus z, because can I take this power in the denominator? Yes. Dz over z the power n plus 1, and then iota I'm taking outside. So this is equal to, I'm taking whole of this to be fz dz. So where fz is 1 over iota e the power minus z over z the power n plus 1. Very fine. Now the poles of the function are given by taking the denominator equal to 0. So denominator is z the power n plus 1. This should be equal to 0. And I get z equal to 0 how many times? N plus 1 times. So z equal to 0 having pole of order n plus 1. So clearly this function has a pole of order n plus 1 at origin. Now to calculate the residue, again I need to apply the formula. So this is 1 over n factorial, limit z tends to 0, derivating n times z minus 0 the power n plus 1 f of z. So this is equal to 1 over n factorial, limit z tends to 0, just write the value for f of z, dz the power n, e the power minus z, 1 over iota I'm taking outside, and this z the power n plus 1 is cancelled out with this z the power n plus 1. Right? This fz, right? Z the power n plus 1 is in the denominator. It is cancelled out with the z the power n plus 1 in the numerator, right? So next, 1 over iota, 1 over n factorial, limit z tends to 0, I have to derivate e the power minus z n times. So this is equal to 1 over iota n factorial, limit z tends to 0. Now here, because this is a e the power minus z, if you derivate this first time, you will get minus of e the power minus z, and then you will get plus e the power minus z. So this should be, I have to write here, minus 1 the power n, e the power minus z, right? And now if you take the limit z tends to 0, put here z equal to 0, so I'm getting minus 1 the power n over iota n factorial. So by Cauchy residue theorem, we get this integral to be equal to integral over c fz dz, which is equal to 2 pi iota times the calculated residue, and I have calculated it as minus 1 the power n over iota n factorial. This iota cancelled with this, so finally I got 2 pi over n factorial minus 1 the power n. Now if you equate the real parts, we get integral 0 to 2 pi e the power minus cos theta, then cos of n theta plus sin theta d theta, right? This is equal to minus 1 the power n 2 pi over n factorial, because right hand side is already in the real part. It is having only the real part, right? So thank you very much. Here ends up two examples. These examples are very important one. The most important thing is to find. The most important thing is to reach from this integration to this integration, right? Furthermore, are already same what we have done so many times in the previous videos. The solutions is step by step, very easy to solve. Just have to make changes over here to get the easier integration, right? Alright guys, thank you very much. Next time we will meet again, and have a nice day. God bless you. Goodbye.